the rate at which particles, which are initially static, so which belong to the bed surface, are entrained into the flow and join the bed. At what's going on. This blurred zone here corresponds actually to the zone where the grains are moving. And if you want a clear picture of what's going on, one way to do that is to compute the difference between two consecutive images. And if you average this difference over a long duration, you end up with the following image, where in black you have the sediment bed, and in white you have the bedload layer. And you can see that the bedload layer, the thickness of the bedload layer is of the order of the grain diameter. So this has, of course, important consequences on the on bedload transport. In particular, it means that bedload transport is primarily controlled by the characteristic of the flow in the vicinity of the bedload layer. And as a matter of fact, we all know that the main control parameters for bedload transport is the Schiltz number, which is related to the shear stress and to the weight of the grains. But you all know that, of course. And so just to illustrate that point, here I've plotted the sediment discharge as a function of the Schiltz number. So the blue bullets corresponds to measurement performed in your experimental device. And we see that, of course, bedload transport increases with the Schiltz stress. We also see the existence of a threshold Schiltz stress below which the sediment transport is equal to 0. And the only thing I want to point out here is that I'm going to focus on what's going on near the threshold of sediment transport. So with other words, I'm going to work within the frame of what David John Furbish defines as the rarefied regime, as opposed to Kimberly, who focused on the concentrated regime somewhere over there. Okay, so now that we have the thickness of the bedload layer, I'm going to say a few words about the average particle velocity. So for a viscous flow, we expect that the particle velocity is going to scale at the fluid velocity in the bedload layer. Now, because the bedload layer is only one grain size thick, the fluid velocity in the bedload layer goes at the shear rate of the flow times the grain size. But in a viscous flow, the shear rate is proportional to the shear stress, which is proportional to the Schiltz stress. So we end up with the following prediction. The particle velocity should scale as the Schiltz stress times the settling velocity. And this is a prediction that can be checked. So here is a figure that I extracted from the paper by François Charus. You're looking at the probability distribution function of the particle velocities. The different symbols correspond to different experiments performed with different value of the Schiltz stress. But the important point is that from those PDF, you can compute the average particle velocity, and you identify that it scales as the Schiltz stress times the settling velocity. Okay, so now we have the average particle velocity, and I'm going to say a few words about the deposition rate. And to do so, I'm going to use another movie. So this time, it's a view from above the experimental channel. It's a slowdown movie. 1 second in the movie corresponds to 0.1 seconds in the real life. And you can see that some of the grains are dyed in black so that we can track their trajectory. So again, this is bedload transport, rolling, bouncing on the bed, and so on. Here is a plot of the velocity of a particle, of a given particle, as a function of time. And when we look at this plot, we see that the particle velocity oscillates in time. And what is more, we see so these oscillations are due to the fact that the particle, of course, bounces on the sediment bed. And each time the particle hits the sediment bed, its velocity drops. It falls sometimes to 0 or almost 0. Now, looking carefully at this data, we see that actually this characteristic bouncing, motion involves a characteristic bouncing time. which actually scales at the grain size divided by the settling velocity. In practice, it's of the order of 10 times the grain size divided by the settling velocity. So now imagine that each time the particle hits the sediment bed, it has a finite probability to remain trapped on the bed. Then if this is the case, you end up with the following prediction for the deposition rate. The deposition rate should scale as the concentration of moving particles, the number of particles in motion, divided by the characteristic bouncing time. And indeed, the experiments confirm that. Now I'm going to end with the erosion rate. So the erosion rate is a bit tricky, but I'm going to try to be very simple here. So the first idea is that the erosion rate should scale with the concentration of static particle on the bed. This comes back to the discussion about sediment availability that Michael was having this morning. Basically, if there is nothing to erode on the bed, then you're not going to have any erosion. That's the idea. Then for the sake of physical dimension, I need a time scale here, and it turns out that the only time scale that comes naturally out of the control parameters of the problem is the characteristic bouncing time or the characteristic settling time that I introduced in my previous slide. And finally, the experiments show that the erosion rate increases linearly with the excess shield stress, and in particular, when the shield stress is below the threshold, of course, the erosion rate drops to 0. Okay, so let me summarize what I've told you so far. So the idea is that according to the erosion deposition model, bed load transport is described by the following equations. This one describes mass conservation in the bed load layer, and then here we have the expression of the particle velocity, of the deposition rate, and of the erosion rate. Now, of course, so far I have considered only the case of a viscous flow, and an obvious question is, what if the flow is turbulent? And so to address this question, you need a bigger flume with a bigger pump, allowing you to reach bigger Reynolds number. And then once you have this big flume, you need to replicate all the experimental measurements that I've presented so far. You need to measure the concentration of moving particle, you need to measure the particle's velocity, you need to measure to track their trajectories, up lengths, and so on. So to make a long story short, we've done that within the frame of the PhD of Luce Malverti, and we found that the nature of the flow mainly changes the expression of the velocity of the bedload particles, but it does not qualitatively modify the mechanism by which the bed exchanges particle with the bedload layer. In particular, the equation for the erosion rate and the deposition rate remain unchanged, or the scaling laws, I should say. And so, as a result, there is a strong mathematical analogy between the equation describing bed load transport in a laminar and in a turbulent flow. And I believe that this is the main reason explaining why so many alluvial structures that are found in nature can also be reproduced in small laboratory experiments. And here I'm just going to give you 2 examples, but I could give you more if I have time. Here, for example, you have a braided river. This is in China. This small dot here is François Métivier, so it gives you the scale of the river. Of course, this is a pattern formed by a highly turbulent flow, but we can reproduce this pattern in a laboratory experiment at a much smaller scale and using smaller Reynolds number. Another example here, these are rhomboid patterns. We are in Japan, the Fue Fuki, I guess, river. This is a bridge, so it gives you an idea of the huge scale of these bed forms. And here you have the same morphology reproduced in the lab at a much smaller scale using, again, a laminar flow. Okay, so I've taken you through a long detour, but now that I guess that we have all the ingredients we need to come back to the question that I asked at the very beginning of my talk. So let's go back to the transport of tracer particles in the lab. And now the question is obvious. Is the erosion deposition model capable of accounting for that? And so to tackle this question, I'm going to go back to the erosion deposition model. So again, I have my bed surface reservoir. I also have my bed load layer. And this time, I'm just going to change one thing. I'm going to dye some of the grains in blue, and these blue grains are my tracers, and I'm going to try to see whether I can predict the evolution of the surface concentration of these tracers or not. And to do so, I'm going to work within the frame of two very simple assumptions. First of all, I'm going to assume that the marked and the unmarked grains have the same physical properties, same size, same density, same shape. So only the color is different. And secondly, I'm going to assume that the total erosion rate of the sediment bed is equal to the total deposition rate of the bed. So with other words, I'm going to assume that the bed is neither aggrading, neither degrading. And so within those assumptions, we can write two conservation equations. The first equation here expresses the conservation of the tracers at the bed surface. And well, this equation simply tells us that the evolution of the concentration of tracers in the bed is controlled by the balance between the deposition of tracers and the erosion of tracers. So nothing very fancy. The second equation describes the conservation of tracers in the bedload layer this time. And again, it tells us that the evolution of the concentration of tracers in the bedload layer is controlled by the balance between the erosion rate and the deposition rate of the tracers. But there is another term here. It's basically an advection term which comes from the fact that the particles in the bedload layer are moving at the average velocity v. So we have a system of partial differential equations. These equations are coupled, and they involve parameters such as the deposition rate, the erosion rate, or the average particle velocity, but we have expressions for these quantities. So we can solve this equation. And here is an example of numerical resolution of this equation. So again, along the vertical axis, you have the tracer concentration. Along the horizontal axis, you have the downstream distance. And so this is the concentration profile of tracers at the initial time. And then again, after a dimensionless time equal to 10, and so on, up to 5,000. And at least from a qualitative point of view, we recover the experimental behavior. We see that as measured as the mass of tracers propagates downstream, it also spreads, it disperses along the downstream direction. Now, in order to try to establish a more quantitative link or comparison with the experiments, I'm now going to focus on two integral quantities. The first one is the mean position of the plume of tracers, of the mass of tracers. So the mean position is just, of course, something like that. And the second quantity that I'm going to look at is the variance of the plume of tracers. So you can think of the variance as the square of the characteristic width of the mass of tracers, which is propagating down the plume. So here is what happens if I plot the variance of the plume of tracers minus its initial value as a function of the mean position of the plume of tracers. And these are not data. These are, of course, the result of the previous numerical calculation. Now, I don't have the time to go into the calculations, but it's possible to show analytically the existence of a crossover between two different asymptotic regimes. The first regime is a short-time regime. You can see it here. And during this regime, we predict that we observe that the variance increases with the mean position of the plume of tracer to the power 3/2. And then there is a there is a prefactor here, but I don't have the time to go into the detail. But the important point is that the prefactor depends on the sediment transport. Then there is a second regime, let's say a long-time asymptotic regime, in which the variance of the plume of tracers increases linearly with the mean position of the tracers. Now, the interesting point is that the short-time regime is actually corresponds to a regime in which the plume, the mass of tracers, spreads following an anomalous diffusion behavior. Whereas in the long-time regime, let's say the mass of tracers spreads according to a normal diffusion process. And this crossover is somehow consistent with the conceptual model that was proposed by Nikora and his collaborator in 2002. We do observe a crossover between two different behavior. Now, of course, we have a prediction, so we need to test it against the experimental data. This is what I've done here. These are actually preliminary results. They are like 1 month old. So here again, the variance of the mass of tracers minus its initial value. Along the horizontal axis, the mean position of the mass of tracers. The blue bullets corresponds to the measurement performed in the experimental plume. And the dotted red line corresponds to a fit of the data with a 3½ power law, so according to the anomalous diffusion regime. And we see that indeed, well, there is a relatively good agreement between the prediction of for the anomalous diffusion regime and the data. The second observation we can make is that, at least in the experiments, we do not see any crossover toward a long-time normal diffusion regime. And at this stage, I don't know why. Maybe the flume is not long enough. I don't know. Okay, so the prediction works for an experiment, then, or more or less, it seems, at least, let's say, it seems promising. So let's try it with field data. So this is what I've done here. So again, variance minus its initial value as a function of the mean position. The blue bullets corresponds to the data acquired in a sandbed river using radioactive sands by Sarah Noble in 1965. And the dotted red lines corresponds to a fit of the data by a 3½ power law. And again, while this field data seems compatible with the anomalous diffusion regime predicted from the erosion deposition model. So, okay, it's encouraging for the sandbed river. What are the gravel bed rivers? So I tried to compare the prediction to the data of accumulated by Colin Phillips and Douglas Jorolmak in the Mamais River, and here is the result. Again, variance minus its initial value as a function of the mean position. The bullets corresponds to the data gathered. Yeah, I'm almost done. Gathered by Colin Phillips and Douglas Jorolmak in the Mamais River. The different colors here corresponds to different experiments. I mean that Douglas and Colin injected several mass of tracers. The first one in 2010, then they injected a second mass in 2011, and I think a third one in 2012, if I remember correctly. So it's actually like each color corresponds to a different experiment or a different field data set. And again, well, it seems pretty encouraging. Power law by a feed by a 3½ power law, and well, the result seems encouraging. Okay, so I'm almost done. I think I'm going to stop here actually and leave you with a few take-home messages, because these are really preliminary results. So the first take-home message is that the experiments show clearly that there is a continuous exchange of particles between the bed surface and the bedload layer. Now, I hope I have convinced you that this exchange plays a very important role in controlling the propagation of tracer particles. And this is happening through an advection exchange mechanism, which actually is reminiscent of chromatography, or Taylor dispersion, for those of you who are familiar with Taylor dispersion. And now, the erosion deposition model predicts the existence of a crossover between two asymptotic regimes. So again, a short-time asymptotic regime, which is compatible with anomalous diffusion, anomalous spreading of the mass of tracers, and a longer time asymptotic regime, which would be compatible with normal diffusion of the grains. But so far, all the experimental data and all the field data that I've been able to gather only exhibit the anomalous diffusion regime, so the 3½ power law regime. Now, of course, this is a work in progress, so there is much remains to be done. In particular, so far, I've totally neglected the influence of diffusion due to the particle velocity fluctuation. So this is something that we actually can implement into the model. It's pretty simple to do that based on the work that was presented by David John Fabish at the beginning of the meeting. Then, of course, also I have considered only the case of a sediment bed composed of grains of uniform size, but in practice we all know that natural streams involve a wide range of different grain size. They correspond to a wide range of different grain mobility, so that's something we need to take into account. We actually started to work on that problem in the frame of, during the PhD of Morgan Housset, and Kimberly has shown you that there is a lot going on that topic, so I expect that we will be able to do better things within a few years. And finally, during all my talk, I have also restrict myself to the case of a river involving a constant flow discharge, whereas we all know that in nature, the flow discharge of a river constantly varies, so there are, of course, aggradation, degradation waves, and I have not taken this effect into account, so it's probably something we need to think of. Thank you very much.
Great, thanks, Eric. Our next speaker, Jeremy Venditti, will present a paper with colleagues from Simon Fraser, and he will talk about bedform structures, patches, and sediment supply in gravel bed rivers.
Sorry, I'm a Mac addicted guy.
The computer does not appear to be on. Okay, so I want to thank, first of all, the organizers for inviting me to come and give this talk. What I'm going to talk about today are bed forms, structures, and patches in gravel bed rivers. And what I'm interested in doing is thinking about basically bed features in gravel bed rivers that are smaller than the channel scale but larger than the individual particle scale. And so there's a whole variety of different bed features that emerge. And I'm interested in focusing on how sediment supply plays into this problem. And in particular, I'm interested to know whether any of these bed features are interrelated or not. As you guys are probably familiar with, in sand-bedded rivers, there's this great continuum of sandy bed forms. With increasing flow strength, we have lower stage plain beds, ripples, dunes, upper stage plain beds, anti-dunes, and cyclic steps and chutes and pools and all these things that happen. But the predictability of that sequence of bed forms is such that it's allowed us to develop these bed form phase diagrams. And the different boundaries between the types of bed forms that emerge are defined by observations. And there's some use in these kinds of diagrams. One of the uses is that they act as a really nice organizing principle for things that we understand about bed forms. And if we understand some of the transitions that happen in here, it allows us to study some of the dynamics. There does not appear to be comparable bed form phase diagrams for gravel bedded rivers, but there is this distinct suite of bed features that emerges. And so I'm sure that you guys are more than familiar with these types of bed features, but I'm going to go through them just so we're kind of all on the same page here. So part of this distinct suite of bed forms that we see in gravel bed rivers includes gravel dunes. They generally occur when the shield stress is well above the critical shield stress for motion of the mixture. Although that's not necessarily all the true. Paul Carling did some nice work in 2006 that demonstrated that you can get gravel dunes form even though you're just above the threshold of motion. But in general, these are thought to occur when you have a really big flow. And presumably their formation and stability are related to the same sorts of processes that occur in sand-bedded rivers. Another type of bed feature that we have in gravel-bedded rivers are bed load sheets. They're basically alternating bands of coarse material here and here with fine material in between and a line perpendicular to the flow. The features migrate downstream via catch and mobilize mechanism whereby fine sediment from this part of the sheet is entrained. That fine sediment finds its way over here into the coarse part of the sheet. It infills the pockets in between the coarse grains. That accelerates the flow velocity in this region. It increases the drag on the particles. and then these large particles pop up and they move on down to the next coarse patch. And so these features then migrate downstream in that fashion. They are assumed to be genetically linked to dunes, but I think the evidence of that is quite circumstantial, and I'll show you why I think that a little bit later. There are also these structural features of a gravel bed that we've heard a little bit at the conference about already, and that Michael Church and Marwan Hassan have written about quite extensively. I'll say, starting out, that clustering of particles in gravel transport is just part of the process. It seems as though, one particular grain size seems to like to find grain sizes of similar sizes and then, fall into the wakes of those, and you get this clustering, and then that cluster breaks up and the particles move on. But as you go through a sequence of that, as the flows decline in a hydrograph, what you do is you get these keystones that drop out of the flow, and they stop participating in the bedload transport. Then those keystones start collecting smaller stones around them and form these accumulation and wake deposits. If you get a bunch of these keystones and they start aligning across the flow because they're sort of jiggling around and moving a little bit, you tend to start forming these transverse ribs that are across the channel. And then if you start connecting some of those transverse ribs by inserting some large stones in between them, you can start developing these reticulate stone cells that Marwan Hassan and Mike Church have written about quite a bit. The last feature of gravel bed rivers that we see are sandy bed forms that develop over a weakly mobile gravel, or sometimes an immobile gravel. Martin Kleinhans did some work on this for his PhD, where he showed that if you have an immobile gravel bed and you increase sand supply to that gravel bed, what happens is you first start getting sand ribbons form or streaks form, and then you get bark-and features begin to emerge. And then as you increase the sand supply, the bark-and features start to link up across the channel until eventually you get bed forms that are laterally continuous. So I think a couple of fundamental questions emerge here, and that is what controls the emergence of these different bed features in gravel bed rivers. And the other fundamental question I want to get at here is, can we predict the emergence of these bed features in gravel bed rivers in some physically based framework? There's been several notable attempts to extend bed form phase diagrams designed for sand-bedded rivers to include gravel-sized sediments. And I think if you look at them, they all seem to suffer from the same problem, in that once you go up here above a grain size of about 1 millimeter, you get all these bed features that are not distinguished by the flow velocity and the grain size, or whatever sorts of metrics you want to put on the axes of these. And these are useful exercises. I mean, Paul Carling used this to identify some of the characteristics of gravel dunes. But I think there's a fundamental problem here, and I think the fundamental problem is that there's an implicit assumption here that the bed features appear on the bed because of changes in the flow strength. That's implicit in the diagram. But bed texture is controlled by sediment supply, and I think to a lesser extent the flow strength. We need the flow strength there, of course, to push the grains around, but the sediment supply plays a very important role in whether or not certain bed features emerge. I think this is really nicely demonstrated in some experiments that Bill Dietrich reported in Nature in 1989. What they did is they supplied a small flume channel with a constant feed rate. They ran the flume to a steady state, and then they progressively reduced the sediment supply to that channel. And so one of the important findings of this investigation is that, as you reduce sediment supply to a channel, the bed coarsens. And the reason that it coarses is because you get the expansion of coarse immobile patches on a stream bed at the expense of more active, finer patches on the bed. We did a little bit of additional data analysis using some of the data that they collected in those experiments in scuba. And what we found is that is so they used a bimodal sediment, and that bimodal sediment produced these bed load sheets, right? And those bed load sheets had coarse heads, and they had fine tails, and the passage of these bed load sheets downstream created these enormous fluctuations in bed load transport. And then as they began reducing the sediment supply, those bed load sheets gradually started to weaken, and the fluctuations declined until they got down to their lowest sediment their sediment feed rate, where the fluctuations are almost absent. And what happened as this was going on with the sediment flux rate is they went from a very heterogeneous bed surface, lots of different patches and lots of different patch types, to a state where there were fewer patches, where again the coarse patches expanded at the expense of finer patches, until they got down to this really low feed rate where the bed was basically uniformly coarse. And so I think what that shows is that having the same hydraulic conditions, you can actually have bed load sheets appear and then disappear based on the sediment supply. I think a really nice example of this process is from some experiments that we did at UC Berkeley, I think about 10 years ago now. And we basically did the same experiment as they did at Scuba, except we decided that we were only going to use gravel, right? We wanted to see what happened when we eliminated the sand from the process. So what we did is we did the same thing. We supplied the channel with a constant feed. We ran it to a steady state. We held the hydraulics constant, and then we started reducing the sediment supply to the channel. And in fact, we actually completely eliminated the sediment supply at some point. And so then what happened is these bed load sheet features emerged. And so if you look at that image and you tell me that you can actually see a bed load sheet there, I would be, you have some impressive abilities that I just don't have. It doesn't look like there's anything there to me. But if you look at the sediment dynamics that are happening here, we do in fact have a tail, a middle, and a head of this bed load sheet. You can see it in the amount of sediment that's being transported at any one time. And you can also see it in how active certain grain fractions are on the bed. And so then we had these bed load sheets that you can't really see looking at a picture, but you can definitely see when you look at the active transport. And it produced a time series of sediment flux that looks like this, right? Where we had several orders of magnitude fluctuations in gravel flux, based on what portion of a sheet was going out of the channel at any one particular time. And just like in the Scuba experiments, as we went to lower and lower sediment supply, the fluctuations got smaller and smaller. And what was happening in hand with that was, we started out at a very high sediment supply, or a high sediment supply in our experiment, with a very heterogeneous bed, right? With bed load sheets formed, and as we gradually reduced the sediment supply, we expanded the patches of inactive coarse material at the expense of the finer material, until we wound up with a bed that was uniformly coarse. So both with the Scuba experiments and the bimodal sediment and with the pure gravel sediment, what we found is that even though we held the hydraulics constant here, sediment supply is what ultimately controlled whether or not these bed features emerged. So if we come back to my fundamental questions here, what controls the emergence of various bed features that occur in gravel bed rivers? I'm going to hypothesize that sediment supply, and to a lesser extent flow, controls them. And then we get to this question of whether we can predict the emergence of bed features in gravel bed rivers in a physically based framework. And I'm thinking about a phase diagram here, and I would say, well, the answer based on what I showed you is maybe. So what I did is I got together a couple of my graduate students, and I presented them with this sort of same reasoning. And I said, do you think you guys could make a bed form phase diagram based on what I told you? And so what they did is they went through the literature. They pulled out somewhere between about 75 and 100 publications that have been written on these bed features. And I said, well, just take them, extract as much data as you can, and develop some metric of sediment supply, develop some metric of the flow strength and grain size, and of course I was thinking of the Shields number here, and make a bed form phase diagram for me. And what they came up with was a dizzying array of some of the strangest bed form phase diagrams I'd ever seen, but they were great because they really explored a lot of different combinations. And so I looked at it and I said, okay, we have something here, we should work on this a little bit further. So the first thing we needed to do is we needed to identify a good metric of sediment supply. And fortunately, Bill Dietrich already did this for us in 1989, where he argued that sediment supply could be quantified with respect to the capacity in the channel. And so what he did is he started out with sort of a basic bed load transport function here, and then he defined this variable here, Q star. And so Q star is basically the shear stress above the critical shear stress for the surface divided by the shear stress minus the critical shear stress to move the sediment load. And so then if you invoke the Shields number here, you wind up with this expression down here for Q star. And so again, Q star represents our supply with respect to the capacity. And so I plotted that up right here against what is sort of a pseudo armor ratio, right? So this is the D50 of the surface divided by the D50 of the load. And we assume that this is an armor ratio because we assume the load has the same grain size distribution as the subsurface material. And what we find is we get basically this asymptotic decline in Q star as we go to higher and higher armor ratios. So that's exactly what Bill found, and what I've done here is I've added our data in from the Berkeley experiments. The other thing I did here was I added in some data from Hassan and Church. And so they did a series of experiments where they basically filled a flume channel up with mixed size sediment, and then they turned the flume on and measured the transport rate, and then they measured the transport rate 96 hours later after the bed armor had completely formed. And you can see that that data set right there seems to kind of have the same properties as these data sets right here. But I would kind of expect, based on the way they did these experiments, that these data wouldn't sit next to our experiments on bed load sheets, but they actually might kind of sit down here a little bit. And so we thought about why that happens, and I understand that Mike Church and Marwan Hassan also struggled with this problem at some point. And they determined that the reason why they sat next to the bed load sheet data is because of the functional form of the sediment transport relation, and in particular the non-dimensional critical shear stress in the Meyer-Puter-Mueller equation is sort of a set value. They found in their experiments that because of the structural arrangement of the bed that value was no longer of use to them. So what they did is they took the fundamental idea of Q star and they recast it. And what they did is they recast it so that it was the ratio of the bed load flux at the beginning of their experiments to the flux at the end of their experiments. And if we do that, what we find out is this new value of Q star that represents the supply relative to the capacity actually still asymptotically declines, but the data that we would expect to sit below it actually does sit below it in approximately the right place. And so the data seem to form some sort of continuum. And so then I thought, well, this is great. Now we have a metric of sediment supply. And then we started out playing around with the Shields number on this axis right here, and we tried a whole bunch of different things. And something dawned on us in the process, and that was that what we actually needed on this axis was a metric of the differential mobility of grain size distributions. The reason being is that the differential mobility of grain size distributions ultimately affects what emerges in terms of the bed structure. I'm sure many of you are aware of this, but there's a whole bunch of different mobilities that can emerge in a gravel bed river, and the terminology that's assigned to them is confusing. So there's things like full mobility, partial mobility, and equal mobility, and then there's partial mobility, selective mobility, equal mobility, and then there's several kinds of equal mobility. And none of the definitions really seem to map onto each other perfectly. So what I did is I went and I took some terminology from Parker in 2008. So if you don't like the way I use these things, you can go to Illinois and complain to Gary, I guess. But so far as I can tell, there's 4 fundamental behaviors of grain size distributions in the transport process. We have partial mobility, where we have the bed load grain size distribution that's somewhat finer than the bed surface grain size distribution, but some portion of the bed surface distribution is not moving. We can contrast against partial mobility selective mobility, where we have the same thing. The bed load distribution is finer than the bed surface distribution, but the whole distribution of the bed surface is in motion in the bed load. Then we have equal mobility with respect to the bed surface, and that is where the bed load and the bed surface have the exact same grain size distribution. And then we have equal mobility with respect to the subsurface, based on some of Gary Parker's earlier work, where basically the bed load and the subsurface have the same grain size distribution, but the bed surface is a little bit coarser. And in fact, if you think about this, equal mobility with respect to the subsurface is basically the same thing as, or it's a special condition of selective mobility. But of course, we have to turn that into a metric that we can put on the x-axis of our diagram. So what we did is we looked at the formal definitions for these different types of mobility, and it seems to come down to the ratio of the fraction of a size I that's in the bed load divided by the fraction of a size I that's on the bed surface. And so for equal mobility, there is no change in that ratio PI-FI across the grain size distribution. For selective mobility, there is a decline in that ratio as we get to larger and larger grain sizes, but that curve does not terminate before we get to the end of the grain size distribution. And then we have this partial mobility curve here, where it obviously does terminate before we get to the end of the grain size distribution of what's sitting on the bed. So then the question is, well, how do we turn that into an index of grain mobility? And so we decided what we'd try to do is we'd try to look at the large sizes and how they're moved in the bed load. And so we said, we defined equal mobility as being when the D84, the grain size distribution of the surface, divided by the D84 of the load is equal to 1, right? So that means we'd be right about here on the diagram. Then we have selective mobility, and any time that this happens, that ratio, D84 of the surface over D84 of the load, is going to be greater than 1, right? And then we had to define partial mobility in terms of the D84 of something. And so what we did is we scoured through the literature and we looked at a whole bunch of experiments. What we found is that people describe partial mobility as occurring when this ratio right here was greater than 2. So we have sort of an empirical threshold there, and that puts an upper bound on our selective mobility index. So this is what happened when we took all the data that we could find and all the data that reported enough information for us to use. We have here, we have our value of Q star, and on this axis here, we have our ratio of the large grain sizes in the load and on the surface. And you can see, I hope, that we've actually segregated out the types of bed features that I've been talking about. Gravel dunes appear right over here. Bed load sheets occur right here. We've got clusters and ribs that are occurring in this area right here. And then we have this sequence of sandy bed forms that occur over gravel on this part of the diagram. And so I think that we have actually separated out successfully the different bed features. So we took this and we abstracted it to make this. This is an alternative bed phase diagram for gravel-bedded rivers. I'm going to spend the rest of the time that I have left here building this diagram for you and explaining to you why things are in different places. So again, on the x-axis here, we have our index of sediment supply, and on the on the y-axis, we have our index of sediment supply. On the x-axis, we have our index of bed mobility. So then if Q star here is greater than 1, it means the supply is greater than the capacity. If it's less than 1, it means the supply is less than the capacity. Here we have our line of equal mobility, right? So in this context, you can't actually go across that line of equal mobility. This is selective transport here, right, from our index from 1 to 2. And then we have partial mobility where we go from 2 to whatever. So the first thing I wanted to point out is that the observations of gravel dunes that we were able to extract from the literature, they all kind of cluster around this 1 point right here, right? So Q star is equal to 1 means the supply is equal to approximately the capacity, and then our metric of the mobility indicates that the transport is approximately equally mobile. And I recognize what this suggests. It actually suggests that gravel dunes are not supply controlled at all, especially if our supply is basically met by the capacity. Then we have the selective mobility regime right here, and I've termed this the domain of bedload sheets. And so what happens here in the domain of bedload sheets is that we would expect bedload sheets to occur under an equal mobility condition, right? Because in order to pass bedload sheets downstream, basically all the grain sizes have to be in motion, averaged over some period of time. But as we decrease the sediment supply, what happens is we move into this selective mobility regime here, right? Where we start leaving some of the coarse particles on the bed in these inactive zones that I described a few moments ago. So the question is what would happen then if you decrease the sediment supply and you wind up in this domain of bedload sheets right about here, and then you start increasing the sediment supply. Well, what will happen is you'll move back up off the diagram through that point right there, and you'll wind up in a condition where the bedload sheets that you see probably are incipient dunes. But most of the time, if you see bedload sheets, they're going to be in this regime right here. It's a nice little bullet point there. Also, as we go through this selective mobility regime, once we start dropping down below a Q star value of 0.1, bedload sheets disappear, right? But that's what we observed in all of our experiments. And so the question is, well, what happens in this region of the diagram? Well, we don't have any observations in there. But I think it's reasonable to assume that you get clusters, stone lines, ribs, and cells developing at these really low supply rates relative to the capacity. But I think what is more likely to happen is if you come out of this domain of bedload sheets, you're going to come into this portion of the diagram right here where you get a partial mobility regime. And you're going to get pebble clusters, ribs, and stone cells start to form. And my placement of these features here in a diagonal is purposeful, right? Because based on Church's and Hassan and Church's papers, they basically describe a situation where first you get pebble clusters formed, then ribs, and then stone lines. And in fact, Hassan and Church did some experiments where they then reintroduced sediment supply to the channel, and it basically went back this way, right? Where you got really well-developed stone cells, you started breaking them up and just getting clusters. And then we have our final portion of the partial mobility regime here. So this is a condition where you've got a sediment supply, but you're in the partial mobility regime, but it's a high sediment supply. The only way that can really exist is if you're feeding sand onto an otherwise weakly mobile or immobile gravel bed. And so in this condition, we get sand ribbons form, we get bark and dunes form over a static bed, or we get sand dunes with gaps in the troughs. So the question is then, well, what happens if you are going through this sequence and you disturb the armor? Well, one of two things can happen. One is you can move up into this part of the diagram here where you're basically burying the bed and you get hydraulically controlled dunes of the kind that Astrid Blom has done some experiments on. Or you can move into the domain of bedload sheets where you go from having these kind of sand dunes, and as you start incorporating more gravel, you start forming something that's a little bit more like a bedload sheet. So, just a few perspectives and conclusions. So the framework that we've defined here seems to separate out the different bed features that we see in gravel bed rivers. due to differences in sediment supply, and that is relative to capacity, and the grain size distribution mobility. The framework that we define here is insensitive to sediment sources because it only focuses on local bed features, right? That is, features that are larger than the grain scale, but they're much smaller than the channel scale. The other thing is that it allows for estimation of the relative sediment supply from some metrics of the bed surface and the subsurface. And so if you wanted to go to the rock record and you wanted to figure out what the relative sediment supply was, well, you can do that. And if you happen to have thousands and thousands of wonderful pictures of gravel from Mars, you could also do the same thing. You could go and look for these structures, you find these structures, you know what the D84 of the surface and the subsurface is, and that will allow you to estimate what the relative sediment supply is. Now, if you actually knew what the sediment supply was, you could actually calculate the capacity that formed various surfaces on the surface of Mars, potentially. The final thing I just wanted to say is that a major impediment to developing this framework and to applying this framework was that we didn't have a lot of data to verify it, right? We went through 75 to 100 publications and only 5 of them had enough data for us to put on our diagram. And of course, that makes a lot of sense, right? I mean, we're talking about like partial mobility and selective mobility, and prior to the work of Peter Wilcock, a lot of those kinds of terminology wasn't really in the literature. So a lot of that information wasn't reported, but a lot of the publications we looked at were published in the last 5 years. And so we should have been able to pull a lot of that information out, and we're unable to. So I think a significant effort really has to be underway, and I think we're all getting pushed into this by granting agencies to start archiving our data. And so we're doing that. We have to do that now. But I think one of the dangers we face is there's also all these great experiments that have been done over the last 50 years, pushed forward largely by this conference in gravel bed rivers, and that data is not archived. And it's really hard to get access to it if you don't actually know the person who collected it. So I'd encourage those of you who do have this data to figure out a way to archive it into one of the national archives so that future generations, my grad students, can have access to it. Thanks.
All right, thank you very much for 2 excellent talks. Yes, I am expecting lots of questions. So David and then Astrid. David, go ahead.
Eric, this question is for you. You know it was coming. I very much applaud the use of laminar flow experiments. They're well behaved in many ways. I like the idea that we are beginning to relax our misconceptions that laminar flows and turbulent flows have nothing to do with each other when it comes to sediment transport. I think laminar flows very much can help us inform a deeper understanding of transport. So now, coming to the question of what you have referred to as anomalous diffusion. The touchstones here are Brownian motion, classic Brownian motion, normal diffusion, in which the diffusive behavior is time invariant. That is, the mean squared displacement calculation survives an arbitrary translation in time, which is not the case of sediment particles which start and stop. And so my question to you is, in your calculation, of the mean squared displacement, do you calculate that mean squared quantity based on all paired observations regardless of the starting point? Or are you using a virtual plume wherein you're setting all particles starting at time equals 0, and then the averages over the particles, not the paired observations? The purpose of my question is, the 2 calculations for start and stop behavior are not the same, and that they reveal different physics of what is going on. Can you comment on this?
I'm going to try. So if I understand correctly your question, you're wondering whether I'm actually averaging the variance of the particle as if they had all started from the same position, or whether I'm considering their absolute position. That's correct? So I'm considering their absolute position. But there is a trick. And the trick is that I have systematically computed and plotted the variance of the mass of tracers minus its initial value. And the reason I'm doing that is because even if you're dealing with normal diffusion, so just random walk, in a random walk process, so you have this Gaussian that is spreading. The initial time doesn't exist. It's only a conceptual initial time in which you would have a Dirac, so an infinite concentration with a zero width of particle at the very beginning of the experiments, and we never have that. So even with a normal diffusion process in the lab, you would have to actually remove the contribution of the initial variance to recover the square root behavior. Am I making sense? Okay, well, what do you want more? So yeah, coming back to the anomalous diffusion process. So basically what we're dealing with, well, at least I feel that what we're dealing with is a sort of chromatographic process. So, in chromatography, basically you have an exchange between a layer of immobile particles. They are absorbed for a while and then they're removed. So within the frame of erosion deposition model, bed load is just another chromatography process, except for one thing, and this one thing is very important. In chromatography, the particles are either moving or they are at rest, but in the case of bed load transport, you have to add the velocity fluctuation, which I did not do in the calculation that I show you. And still, we observe this spreading process. So the question I'm trying to pondering now is whether I need this velocity fluctuation or not to account for what we observed. I don't know if I answer your question or not.
All right.
Thank you.
Astrid.
Astrid Blom, Delft University of Technology in the Netherlands. I have a question to Eric. I expect that in the field there is another mechanism that would contribute to the streamwise dispersion of particles. And I think it is the temporary burial of particles within the bed. It is not incorporated by your model, neither by the model of my neighbor that just disappeared, David Furbish. And I think Crickmore and Lean were the first to do some pioneering work on this in the 1960s. Could you elaborate on this temporary burial of particles and how it would affect the streamwise dispersion of particles?
Okay, so yeah, so perfectly right. It's going to play a role in the field, and actually it also does play a role in the experiments. So first of all, what I would expect from temporal burying is that it would increase, of course, the rate of dispersion, because you're going to increase the difference of effective velocity between the particle that is somewhere below the surface of the bed and that is going to be trapped here for a long time, and the particles that are moving at the surface of the bed. So I don't have a complete answer to your problem, but let's say I have at least one comment that comes out of the experiments. In the experiment, we're actually facing the same problem. When I told you that the way we introduce the sediments, the tracer sediment, is rather crude. We use a spoon or something that is very like a spoon, and we just pour the sediment into the river. So when we do that, at the beginning of the experiments, we have a sediment bed that is at equilibrium, perfect equilibrium, no aggradation, no degradation. But then when I pour my tracer sediment, I actually build a small mound at the surface of the bed. And so it means that I'm not actually starting within ideal conditions within the ideal conditions of my model. I don't have a thin layer of particles, I have a mount of particles. So some of the particles are actually at the surface, and some others are buried. The way I get rid of that problem is by actually removing the initial value of the variance from the data. So once again, I always plotted variance minus initial variance, which is a way of getting rid of the particles that are never going to move because they're actually buried in the bed. I mean, you can see them because, of course, a sediment bed is not a flat surface. You can guess them, but they're not going to move.
All right, at the risk of being accused of being a leftist, I'm going to stay at the left side of the room.
Oh, yeah.
Over there.
We don't want to be leftist.
Yes. Sorry, I don't know the name. Next to you, Astrid.
Dave Milan, University of Hull. Question also to Eric. Two parts to my question. You showed your model of dispersion, and your flume experiments were based on a uniform bed. I just wondered how that might translate to a natural situation where you have large bed forms, such as pools and riffles, so how the dispersion might vary over bed forms. And secondly, you used you mentioned two field validations, the one by Hubble and Sayre, which was a sandbed river, and the other one, I think was Phillips, which was looking at dispersion of gravels. In gravel bed rivers, very often you've got two phases of transport. You have you can have phase one sand transport over a stable gravel bed. So I just thought, how might your model of dispersion relate to a situation where you've got sand moving over a stable gravel bed?
Okay. So the first question deals with bed forms. So it turned out that the erosion deposition model was first developed by François Charus in order to predict the wavelengths of ripples in a laminar flume experiment. And so I have no time to go into the details, but I have put, the paper contains more information on that aspect. But the idea is that within the frame of the erosion deposition model, so the sediment flux is controlled by the balance between erosion and deposition. However, it takes a finite length for the sediment flux to adjust to an abrupt change of flow condition. Something called the deposition length. I don't know if it's of the order of a few dozens of grain sizes, depending on whether you're turbulent or laminar. But so anyway, the idea is that the erosion deposition model actually incorporates the non-locality of sediment transport that you need to correctly predict the wavelengths of ripples. So I hope that answers your first question. If you want to know more about that and look at the stability analysis, I would recommend you to look at a paper by François Charus in Physics of Fluid in 2006, where he actually uses the model to compute the wavelengths of bed forms. Now the second question was basically about what happens if there are two different grain sizes, right? So I don't know about sand versus gravels, but during the PhD of Morgan Housset, we tried a very simple experiment where we would have, so it was only sand, but we had two populations of sand. If I remember correctly, that was like 1 millimeter and 5 millimeter or something like that. And we check whether the erosion deposition model still applies to the propagation of the grain, to the sediment transport. And so we published that in a GBR paper in 2012, I think. But the general idea is that the general framework still works, because actually the rate at which you are going to erode the grains of the family number 1 or the grains of the family number 2 is going to depend on the relative proportion of these two families. So you keep that. And the only thing that was different was the threshold of grain entrainment, which depends on the relative proportion of both particles, following a linear relationship. So that's about as far as I stand right now with respect to this problem.
John?
interesting presentation. And I also find some of your previous papers very interesting, and I've been following them. The question that I have is related to the diagrams that you suggested, but also with that respect to having a D84 for any gravel bed river channel. Now, one of the things that you have shown in your previous papers, and some others have also, is that gravel bed rivers do not have a uniform size distribution. They have patches. So one of the questions that is related to your classification is, if you have a D84 of a river reach, and that relates to, in fact, any bedload equation, to what does that average mean? Is it to a patch that is very different from another, and in many rivers they differ substantially? That is the first part of the question. And the second is that in many gravel bed rivers, especially if there is in general a high supply of sediment, and unlike conditions that are very uniform in flume, all these different patches occur simultaneously in the same river reach at different locations. So that it would be appropriate and relevant to what you said that for a given discharge, you could have any of them. But then it would also mean that in different parts of the river, you could have clusters active and also gravel sheets, etc. So it would be interesting to see what you think about that. Thank you.
Yeah, that's a tricky question. So, I mean, in some of the work that we did previously when we reported grain size for, you know, surface or bed load, well, actually mainly for the surface, what we would do is we would actually measure the grain size of all the patches, and then we would aerially weight the grain size that we reported based on how much of the bed was covered by a particular patch. So, I mean, that's one approach you could use to try to understand how to spatially average things for a reach. I think the question about what to do with this kind of classification when you've got patches that are representing everything in the reach, I think the answer to that is, well, if you look at any one of those patches, that's probably the scale at which you should be applying this kind of thing, right? So if you look at a patch and there's clusters formed in a particular patch that are stable, and then another patch there's bed load sheets, it's really a local classification of what the transport regime might be like in a particular place. So you could have the sediment supply conditions that you would predict from this sort of framework might vary from place to place in a gravel bed river, particularly in a high supply river. A lot of the things I think about, though, are relatively low sediment supply rivers, because I'm from British Columbia. There's just not a lot of gravel that's going into those channels, and so a lot of them are very low sediment supply channels compared to something, you know, that you might see in Israel or something like that. So I very much kind of think about, skew my thinking towards those lower sediment supply channels. When you have that higher sediment supply, I think you need to confront these problems about what exactly you would do on this patch by patch kind of basis. Yeah.
Okay, Joel and then Thanos.
Hi, Jeremy. I'm just curious about step pools and pool riffles and things like that. And I can certainly think of some reasons why it would be challenging to have data to put them into this sort of framework. Do you think that they would fall in, you know, where do you think they would fall in your diagrams? And do you think that, you know, the fact that they arguably kind of depends importantly on the interactions with the boundary of the channel, you know, kind of how much do you think that matters or not for, you know, for them?
So I would think that they would fit nowhere on my diagram, because I think that those are channel scale features. And so then if you looked at the sub-channel scale, you might be able to apply this kind of framework to it. But the framework's not designed to be applied to the larger scale, right? So I wouldn't think it would apply anywhere. And I think actually adding those in there, I mean, I thought about this because we, of course, had data that we could have inserted here, but we really had to draw that distinction, right? That we had to go from particles to the subchannel scale in order to understand what was going on with the bed features. Because these bed features can occur in all different types of channels, right? Riffle pools, step pools, and these kinds of things. There are some features, those ribs that I talked about, that are, so some of the early literature talked about these things called transverse ribs. And those transverse ribs, I think Alan wrote some stuff on this, and there was some earlier research before that. That describe these ribs, and they describe them happening under supercritical flow conditions, right? And the idea was that, you know, you get a supercritical flow, you get a wave set up, and then underneath that wave you get a bunch of grains grouped together, and then that wave would go away, and that was the bed form that you were left with. The ribs that I'm talking about here are not that tight. The stuff, you know, in that picture of that creek in British Columbia, that has never gone to a supercritical state. And so you always have subcritical conditions. The step pools and things like that, of course, they can have supercritical flow conditions. And if you look back at some of the original work that was done on transverse ribs, if you look at the pictures, we'd call them step pools now, right? So we've tried to kind of clear out that channel scale stuff from our diagram.
I guess I don't necessarily see why, or I don't necessarily see why you would have to clear it out. And you know, I can certainly appreciate the cleanliness of, you know, kind of not having it in there, but you know, I didn't see anything in there that necessarily meant that it would be a bad thing to put it in there. You know, and certainly the, you know, anti-dune formation has been proposed and seen experimentally for the formation of step pools, but lots of other mechanisms have been seen experimentally too. So it seems like they could fit in there.
Yeah, so I mean, my response to that would be, we're trying to look at these, basically what's going on with the bed features, right? So if I were to go to a sand-bedded river, I wouldn't go and find out that there were sand dunes there and then go, this is a meandering river, right? There's no continuum that's proposed for that kind of thing. And so I was trying to propose a similar sort of structure where we stayed away from the channel morphology scale stuff. I mean, maybe you're right, maybe there is a way that it could be integrated into this kind of format. Yeah.
Okay, so two excellent talks, and actually I enjoyed both presentations. I got a question for Jeremy. I think you raised some very good points about you know, relative mobility, and I agree to a large extent that sediment supply and bed architecture or configuration dictates what's happening in the channel. But I think we have done a very good job looking, you know, in bed load transport prediction. We have done a very good job looking recently about relative mobility, but we have not viewed the flow with from the same spectrum. And what I mean is, like, we have relative mobility, with the same token, we have relative intensity. And when we talk about, let's say, turbulence, then we have the fluctuating component, and the ratio of the fluctuating component with the mean flow, in some ways, it's an expression of that intensity. So I wanted to get a little bit your thinking about this, and maybe that relative intensity can explain the local features that we see in channels and some of the stuff that John Laron mentioned about. And what do you think about it? And
yeah, I mean, I'm obviously very interested in turbulence. I do stuff on turbulence and coherent flow structures, and I see that, I mean, the features that we're identifying here, I guess the question is do you need turbulence to form some of these things, right? And so there is some very interesting stuff that I think her name was Selena Tribe did some simplified modeling that she did where she included nothing about the flow and was able to produce the same structural arrangements of gravel beds that we see in gravel beds. So, you know, the question arises, do you need turbulence in order to do that? And I think it probably depends on the bed feature, and it also depends on the type of patch that you're looking at and the characteristics of the patch. So,
yeah, and I believe it depends also, you know, where you are in terms of the sediment supply regime. So prior to a certain threshold, maybe turbulence plays a very important role. But beyond that point, probably, in terms of sediment supply.
Sure.
But beyond that point, probably the importance, you know, ceases.
Yeah, I mean, the more grains you have moving, the more likely that turbulence is going to be important for how those grains are moved around on the bed and how they're arranged on the bed, right? So, I mean, I'd agree. Yeah.
Paul, followed by over here. I'm sorry, I don't know the name.
I really liked this presentation. I thought it was very thought-provoking. And I wondered whether you considered the temporal evolution of some of these features, because you can have a constant supply in a flume, and some features will form spontaneously across the bed, and others take time. So what I call bed defects, and you might call a cluster in this context, forms spontaneously under a certain flow condition, while transverse ribs, as you define them, and rectillate patterns take time.
Sure.
But the supply rate is not changing, except locally, of course, because of the presence of the obstructions to the flow.
Sure. Yeah. I mean, so the framework does kind of make that assumption that everything's in equilibrium, right? And nothing is really in equilibrium in the field. So some of the structures do form instantaneously. Some of them take an enormous amount of time. I think when you get down to that part of the diagram where you have really low relative sediment supply and you're in a partial transport regime, you're probably going to get that happening in rivers all the time, right? And so that's probably pretty stable. And I think that, you know, when you get bed load sheets emerge, they also emerge very, very rapidly. And when I think about dunes anyways, the sand dunes that are formed over a gravel bed, I also don't think that time scale comes into that problem there. So then I guess my answer to it would be, well, dunes can take a long time to form unless you're at a really high shear stress. And so you might find dunes that wouldn't fit into the framework properly because they had evolved over a long period of time from defects. You might find that you know, some of the clusters that are sitting on the bed are from a short period of time, right? They developed, the flow slowed down and stopped. So I think it really comes down to, when you start thinking about longer time scales, is how well developed are these different structures, right? So how long or how well developed is, you know, the cluster? Is it, you know, sort of with all the imbricated particles on them, or is it just a collection of particles? And I think the degree of imbrication of the features is probably reflects the time scale. So the time scale kind of has to come into play here when you start thinking about this and how to apply this, you know, to these environments where you have hydrographs. Because of course, what you see on the bed is literally a reflection of the last flow that was capable of moving particles. So I think that has to be rounded out into the picture when you're trying to apply something like this or further develop it.
My question is for Jeremy. Thank you for your impressive presentation. And I follow your research for a couple of years. And I already read one of the conference paper you published in Riverflow in 2012 or something. And you already proposed such kind of diagram. This is an improved version. And in that diagram, the horizontal and the vertical axes are the flow strength and the ratio of the sediment supply to the sediment capacity.
Yeah.
And in today's the diagram, the vertical axis is also the ratio of the sediment supply to the sediment capacity. So my question is, you mentioned the sediment supply is more important than the hydraulic conditions. So your experiment are fading experiment. What if just a simple flume experiment is a recircular experiment? You keep the sediment the same, and the water depth is constant. You just increase the flow discharge gradually. You will find the gravel sheet, gravel dunes, what kinds of the forms. You even not change the sediment supply, which means you just change the hydraulic conditions, and you have also can find what kind of the bed forms.
Yeah. So I did. I went to a conference, I guess, like in 2008 or something like that, and I drew a diagram sort of like this by hand, there was no data involved in it or anything. It was just an idea. And so that's what I started with when I started this. And then once we started getting data together, realized that it didn't make any sense. But I think going back to your question about, so if you have a recirculating flume, and if you just increase the discharge and kept everything the same, what would happen? And I think we have to be a little bit careful there, right? Because if you have a recirculating flume, as you increase the flow or the discharge, what you're going to do is you're basically taking what's coming out of the end of the flume and recirculating it. It's coming back in the other end, right? So when you say you're not changing the sediment supply, you are changing the sediment supply. The sediment supply is connected to the discharge, right? And so if you want to, I think about the way a real river works, is that a real river doesn't take the sediment coming downstream and then pile it back upstream again, unless you're in California and they do it with a bulldozer. You have to separate your sediment feed from your sediment flux, and in that condition, this is the kind of diagram that you could produce. I don't know what kind of diagram you would produce if you sort of link together the flow and the sediment supply. I suspect what you'd get is you'd get a hydraulically controlled situation, right? You'd get the kind of bed form phase diagrams that you see for sand-bedded rivers.
My question is hard to say whether the sediment supply is more important or the hydraulic condition is more important. In my opinion, both the sediment supply can present such kind of different forms. And if you just change the hydraulic condition, you can also find what such kind of better forms. So I'm not sure how can you make sure which one is more important.
Yeah, well, I'm not sure you can, right? I think that the framework that we're working with here is, we're saying that you have to have the flow there. It has to be above a critical threshold to move the particles, and it can be to the point where you get equal mobility, selective mobility, or partial mobility. So, I mean, it's not that the flow is not important. It just turns out that something that we have ignored for a very long time is the sediment supply when it comes to forming these bed forms. And I think that's more the point that I'm trying to get across here, is not trying to say the flow is not important, because the flow, I just think that, when we talk about the flow, we have to talk about the sediment supply at the same time. And if we fail to do that, I don't think we can predict much.
Okay, I'm going to give the microphone to Mike Church to make a comment. We are going a little over time, with your permission.
My name's Church. I applaud Jeremy's presentation because it gives some purpose to some of my past random activities. But what I want to do is emphasize that sediment supply is the dominating factor in this problem. When Jeremy talks about the capacity as part of the reference, or the sediment capacity as part of the reference, he's talking about a conceptual quantity related to what sediment would move if you had the power to move the subsurface material. The actual sediment supply controls what actually happens on the surface, because what happens on the surface is the surface adjustment so that resistance is changed such that the actual transport corresponds with the supply that's coming in. And at various stages, the development of sequentially clusters, stone lines, and ultimately reticulate cells are means of surface modification to throttle the actual transport capacity back to the supply. So it's a means of reestablishing equilibrium in the stream. And short of actually changing the elementary fact of changing the grain size on the surface, it's the most rapid adjustment that the stream can make to changing conditions.
Okay, and one more comment in the back by John Buffington.
John Buffington, Forest Service. I'd like to follow up on what Mike was just saying. I agree entirely. You started off by showing a regime diagram in sandbed rivers, and there, as you increase the flow strength, you're getting deformation of the bed, which is a roughness response. But a difference with what you're talking about, most of the features you talked about are not bed forms per se, but as you emphasize, they're particle interactions. And so I guess this is just a comment that in addition to response to sediment supply, I think an important element of this is understanding the particle interactions. And except for maybe the sand ribbons, that's the only one that's not a strong particle interaction. But it just seems to me that's a missing component of really understanding these forms. Because if you don't have the right grain size distribution, of course, you're not going to develop some of these structures that you're seeing.
Yeah. I mean, I agree entirely. The key to understanding these, I think, lies in understanding the particle interactions. And we've done a bunch of work. I mean, the experiments that we've done were basically to try to figure out what some of the particle interactions were, to try to figure out how to like mobilize gravel surfaces and how to rearrange gravel surfaces due to particle interactions. So I would agree completely that going forward from this point, if we want to understand the processes by which these things form, it's all about the grain interactions. And just along the lines of Mike's comment, that I think the big difference between sand-bedded rivers and gravel-bedded rivers is that gravel-bedded rivers, in my mind anyway, seem to have this ability to adjust their surface structure without actually going into whole-scale deformation, right? Whereas sand-bedded rivers, the shear stress is so far above critical most of the time, you're basically getting all these really cool deformations of the bed. Where that doesn't really happen in gravel bed rivers because the surface can actually adjust to the incoming sediment supply to pass it. Yeah.
Okay, well, I hate to cut this off, but I think we all would like some coffee before the next session at 4 o'clock. So thank you again to our excellent speakers.